All right. Welcome back to the last part of chapter 6. We're just going to basically just be on the computer. There's not going to be much math. There'll be a few equations, but if I have assigned a homework problem with these equations, then please let me know. Just because I just want you to know about them because we should be aware of them, but I'm not going to test you on them because everything at the beginning of the chapter is more important with regards to the math. The concepts are important here, but the math was important at the more important at the beginning of the chapter. So we're going to look at the kinetic model, or the kinetic molecular theory helps us model how gases behave, right? This is the simplest model for the behavior of gases, of an ideal gas. Let me say that. So there are three common parts of this theory. The first part is that the size of a gas particle is negligibly small compared to everything else, and the volume that it's found in, right? The gas particle is so small compared to everything else. The average kinetic energy of a particle is proportional to the temperature in Kelvin, right? We talked about this, that the higher the temperature, the faster, the more kinetic energy that these particles will have. And then the collision of one particle with another or with the wall is completely elastic, right? So as it hits, it will all automatically just bounce away. Whereas an inelastic collision is where it hits and it just stays stuck. And so these are just three things to keep in mind, because what we can do is we can, and then use the ideal gas law, because we're talking about an ideal gas. We can use these to determine the relationship, right, between that theory and the ideal gas law. And so here I'm just showing you the number of collisions is proportional to the number of particles within a specific area, and within a specific area, V delta T. And so then we have the volume times the density of particles. If we were to rearrange that around, we could get to the ideal gas law. Again, the ideal gas law is just so powerful. We can describe how the relationships we saw before can be explained using this theory, right? That depending on the temperature, right, it's relational to the energy, and vice versa. But I just want you to just be familiar with it. The temperature we talked about can the kinetic energy of the gas, but it also can determine the velocity of a gas, what's known as the molecular velocity. This is the root mean square of the velocity. It's the square root of 3 RT divided by the molecular weight. And so what the main important thing I want you to focus on here is that it's an inverse relationship between the temperature and the molecular weight, right? And so the velocity of something, right? That little U RMS, it's actually mu, but that doesn't matter. That little micro sign RMS is inversely proportional to molecular weight. So the heavier a gas is, the slower it is velocity, and you can see that in the table. And so one of the ways that we can determine how fast something goes is whether how much it weighs, right? And so I might give you a list of gases and say, okay, which one would be the fastest? And the best way for you to then do that is to calculate the molecular weights of all those gases. The heaviest one will go slowest, the lightest one will go fastest. Based on the movement of gases, we can determine their rates. Mean free path is just the average distance that a gas goes between a collision, right? If you decrease the pressure, if you decrease the volume, you bring those gas particles closer together, that mean free path will decrease. Then we have diffusion. Diffusion is if I were to put in the corner of my office an open can of air spray or something, and how fast would that gas permeate throughout the whole room. Effusion is a process by which a gas escapes from one container to another through a small hole. And you can see the picture there. The ratio of effusion rates of two different gases is known as the Graham's law of effusion, and that's what's shown here. You will not, again, need to calculate it. We just need to know what diffusion is, what effusion is, and then mean free path, how it's the path length with which a gas can travel before colliding it. All right, so then we've been talking about ideal gases, right? We've been looking at the ideal gas law. Everything up to this point, we've talking about ideal gases. But what about non-ideal gases, right? Gases in the real world. What we can see is the actual size of the gas molecule becomes very important at high pressures, right? So if we were to compress a gas down to very, very small volumes, which would be very, very high pressures that the actual size of a molecule is important. And the reason why is because there's things called van der Waals interactions. You guys will read you will learn about these in general chemistry too if you stay on. And they're just they're transient interactions that occur. But what we can see on this graph is the red is an ideal gas, the green is argon. At very, very high pressures, it starts to deviate from an ideal gas because of the molecular interactions. Same thing with temperature, right? Same thing with the temperature. At very low temperatures, we start to deviate from an ideal gas. Now, why do you think that would be, right? What does, a lower gas or a lower temperature and high pressures have in common? That's right, that they increase the interaction between gas molecules, right? So if you're at a high pressure, you're really close volume, that the idea of you interacting with another molecule is a lot greater than if we were to have a bigger volume with lower pressure. Same thing with temperatures. Temperatures do it instead of a volume way, they do it with just you slow down the movement so that when two gases hit, there's a little bit more of an interaction between the two molecules. It's not as completely elastic as what an ideal gas would be before they separate. And so how do we correlate with this? We just add a few different factors to the ideal gas law. So we correct for particle volume and we correct for those intermolecular forces. Now, if you're looking at this equation and thinking, oh no, don't worry about it. We're not going to be calculating non-ideal gases. That's for a different class at a different time at a different level. We're just going to stick with those ideal gases. But I just want to show you that we are looking at ideal gases. Not everything in the real world is as ideal as we like to think it is. And so this ends chapter 6. Again, just focus on the math and the equations that we talked about before this. But I just wanted to introduce you guys to a few other things about gas movement and non-ideal gases.